All right, it's 12:45. What I need you to do is I need you to stop what you're doing, and I need you to open up your digital textbook to 4.1, which is page number 90. In your ISM book, what I would like you to do is I would like you to turn to the page after your test that you have labeled. Remember, in your table of contents, you're going to write down the reading today, sample problems, and then I'm going to give you a free body diagram handout. Okay? Everybody's already copied this down. If you haven't, please copy this down. So what we're going to do now is we're going to talk about what force is, and we're going to look at things we have done in the past and the things that we're going to be doing in the future. So if we're talking about a force, that means something that makes an object move. It is a push or a pull, which in physics we're going to refer to as a vector. And when we're talking about a vector, it's a force that has magnitude and direction. So an unbalanced force causes something to move. So for example, if I had this textbook right here and I set it on the desk, is it going anywhere? No. If I take my hand and I push it, is it moving? Yes. So what we're going to be doing now is we're looking at the movement of that textbook. So if we were doing our dots, remember how we did that and we did it for acceleration? What's happening is this book is here, but it starts off slow, but then it picks up really fast. How do we know that based on this diagram? What are we looking for? To prove that the object is moving faster.
Time versus distance.
Yes, but we can tell by a vector length, right, guys? So the vector length of this, as you can see, nothing starts, gets bigger, bigger, and then a whole lot bigger. Acceleration is showing me at the same rate, but we know that it's accelerating quicker as it goes across. Okay? So the next thing I want to talk about is I want to talk about us doing these diagrams that we're going to start doing starting today. So in your book, it shows you 3 scenarios, okay? It shows a book that's sitting on the table and somebody's pushing it, right? So they're doing force diagrams. To be able to do force diagrams, you have to find a system. What does it mean by the word system? What is a system?
Like you gotta find like a way to do it.
The object that you're zooming in on. Because right now, you have a table, you have a book, and you have a person's hand, right? And so I have to define the system that we're diagramming, okay? So the system we're diagramming is just the book itself. To be able to show a system, you would put a dot around the object that you're doing, okay? So say a book is just stationary, staying seated. So what we're going to do is we're going to diagram these, and I'm going to do these with you. If you have them, then that's great. So if I have a book and somebody's applying force, first thing I'm going to do is I'm going to say, this is my system, which is the book. What kind of forces is acting on the book as it's sitting at the table? What kind of forces?
Gravity.
Well, we do have force gravity. So the way that we're going to do it in this class, we're going to do Fg, that's force gravity, on the book by the earth. Okay? Force gravity on the book by the earth. Now, is the book falling to the ground? Because it's just sitting on that table, right? What other force is there that's counteracting that force gravity?
Force of the table or the desk that it's sitting on.
Yes, and it's called a normal force. Whenever something's sitting still and not falling or flying in the air, it's a normal force that's keeping it there. So it's force normal on the book by the table, is what you said, right? Besides that, I'm applying a force, right, to push the book to the side. Now, are these two forces the same?
No.
Okay. If they wasn't the same, say gravity was more than the normal force, the book would be falling very, very slow. Say the normal force was bigger than the gravity, it would be lifting up off the air, off of the table. Since it's not doing either one, they cancel out. And that's what I want you to do. Draw a line that says these two cancel out. Okay? The other thing that's happening is you said I have a force applied, right? FA, which is force applied on the book by the hand. Okay? You get it so far? Force applied is on the book by the hand. Is there any other force? Nothing that we know of. Say the table was sandpaper. Would there be a force? Where would it go? Where would the vector go for that force of the sandpaper as I'm trying to drag it across?
Side to side.
Okay, so it would be opposite of the applied, right?
Yes, ma'am.
So force of friction on the book by the table, right? Which would be the table has sandpaper on it. Now, if I went through and I made this the same direction as that one, would the book move? No. No. Do you see what I did here? I put one mark through it that states these here make it say it's not moving at all. But now I'm putting two marks that said these two are opposite forces. Do you understand? Because this is very vital for you to understand today. When you're talking about vectors, you have to show direction and magnitude. When you're applying these forces, you have to state that it is. If, say that there was no force at all, and I took this off, I would take these off, and this is what I would have, and that would tell me I have a net force of what? What is my net force? What is net force?
Right.
It was on the next page. And what it is it's a total of forces that are applied.
So it's all them added together.
Correct. So these two cancel out. So my net force would be in that direction, right? That direction. These two cancel out. This one goes there. That's my net force. Do you understand?
Yes, ma'am.
Okay. Now, another scenario. A book hanging by a rope. So our system is still the book. So what kind of forces do we have for that book that's hanging on a rope?
Force of it on.
Huh?
Like the force of the book hanging down.
Okay, so what's causing the book want to fall?
Gravity.
Gravity again, okay? So we've got force of gravity on the book by the earth.
Yes, ma'am.
What other force do we have in the opposite direction? Because it's not falling.
Force of the book on the rope.
Okay, so we have what's called tension force, tension, and you don't know any of these yet, so you're okay. Force tension on the book by the rope. They cancel each other out.
The FT and the FG do.
They do, right? So I'm going to put a mark in between here because it's just hanging. If there was a pulley up top pulling the rope up, then of course this might not be equal, right? That means the book is going up, isn't it? What happens if the rope is on a spring? It's going to go down to however far it goes, and then it's going to stop.
Mm-hmm.
But right now, it's just hanging, okay? The third scenario in the book was talking about a book that's just fallen. How am I going to do those vectors?
It's only moving in one direction.
Okay, so here's my book.
Mm-hmm.
Which direction is it moving?
Down,
Down, okay? What kind of force makes it go down?
gravity.
Okay, so it's force, gravity on the book by the earth. And that's it. If you get this concept of how to draw these, you will not have any problems. But from now on, we're not using the dots anymore. We're not using the vector decoration. We're going to actually do this right here where we're actually showing you a force diagram. Is everybody good? Let's go to the practice problem.
What, the ones on page 93?
Uh-huh.
Is that gonna be going on the sample problem page?
Yep. So what I did here, Jarrett, is I went through and I labeled all what's on the board. I also laid a little bit more of what they showed in the book, but I'm not going to go over that today. I'm going to let you do your own notes because I had one with the person with the ball in their hand, right? And I didn't do that one either on the board, but I'm going to let you do that yourself. So we can talk about it though. If I have this Expo marker in my hand, and we say the system is the Expo marker, what kind of forces are applied here?
The force of your hand holding up the marker?
Yep, and?
The force of gravity wanting to pull the marker down?
Yep, and are they equal?
Yes.
Yes, they are, because it's not falling. If they wasn't, this would be going up or this one would be going down, right? Either the force applied that I have or the force of gravity. Okay? And that's what they were talking about there. The last thing that it talked about, it was talking about two people. If you have one person on this side, one person on this side, and you have a table in the middle, and you have both those people applying a force, what would our net force be?
It'd cancel out because they're both going towards each other.
It would depend on how much force was applied. Say it was me and my granddaughter. Which way do you think it would go?
Her way.
If I'm forcing, I have bigger force, right? I would push her out of the way and the table would go that way, right?
Yeah.
It would be my force, not hers. Say it was me and a big, huge football player. Well, depending on how strong I am, I think he'd be stronger. I'd go the opposite direction. And it was just talking about how they cancel out. Are you good so far? Now, if we think of the analogy of a softball or a baseball, there are three ways that a ball can change its motion. What is the three ways a baseball can change its direction?
When it gets hit,
When it gets hit,
when it gets thrown,
when it gets thrown,
and when it's caught.
when it's caught. Right? That ball changes direction depending on what's happening. So if I'm throwing the ball and we're looking at a ball and you're going to look at the ball at a certain system or a certain time. Say if we're talking about, we're looking at the ball when the bat hits the ball. What forces are on that ball when that bat hits it?
The force of the bat,
So here's the ball.
or the force of the person swinging.
So we have a force that's applied, right?
Mhm.
So it'd be on this side, wouldn't it? Force applied on the ball by the bat, right?
This way.
What else would happen to the bat? What other forces would happen?
Gravity
Okay.
on the ball.
So we got forces of gravity on the ball by the earth. What other force?
Force of the pitcher throwing it.
Okay. So there is a force applied there by the pitcher, right?
Yeah.
Force applied on the ball by the pitcher. Anything else? That's about it, right?
Mm-hmm.
what's happening to the ball?
Changing.
It's going back towards the pitcher.
Yeah, but barely, right? Because he hit the ball and he hit it harder than the pitcher actually threw it, but gravity's just as equal as that one. So it's a bunt. You understand?
Yes, ma'am.
Bunt scenario. Okay, so let's look at the questions that they ask us in the book. So I do believe the questions in the book is on page 92, I think. No, 93. Okay, get your boards out. It's in your desk. I would like you to draw scenario 1 on your board, please. So it says, a skydiver falls downward in the air with a constant velocity. The air exerts an upward force on the person.
So you want us to draw which one?
You're drawing number 1. It says, for each of the following situations, specify the system and draw a motion diagram and a free body diagram. Label all the forces of their agent and indicate the direction of acceleration and net force. Draw vectors of appropriate length, ignore air resistance unless otherwise indicated. Okay, let me see yours when you get it done. Okay, all right. Looks good. Perfect. Okay, so the first thing I did is I drew the skydiver stating he's my system. I also, on my paper, I think I actually even did the airplane. Okay, but that has nothing to do with it. We're just looking at him, right? He is going to be falling down for velocity. His acceleration will be constant at 9.8 meters per second. And so his resistance on the diver by the air and the force gravity on the diver by the earth. Questions? Good? Let's look at number 2. Number 2 says, you hold a softball in the palm of your hand and toss it up. Draw the diagram while the ball is still touching your hand. Well, if the ball is still touching your hand, right? So there's my ball still touching my hand. And if we're looking for the ball as our system, so we have force normal on the ball by the hand. We have force gravity on the ball by the earth. Are they equal?
No.
No.
the hand has more force.
Says you hold the softball in the palm of your hand and toss it up. Draw a diagram. So it's not the same. So what else do we have here beside the force normal? We also have a force applied on the ball by your hand. Now what's the net force? Up in a positive direction. Why? Because my force normal and my force gravity cancel out, but my force applied makes it go up. All right, so the next one says, after softball leaves your hand, it rises up and slows down. Okay, so what happens here?
The force applies, it decreases, so it slows it down.
Well, it's left your hand, right?
Yeah.
The force of gravity.
There's
is
no
here.
force normal left, is there? Force of gravity's still there though, right?
It's not.
But your force applied is up. What would make it stop? What would make it come back down? Besides gravity force.
When it hits its maximum height.
Yep. And then what makes it come back down? Air resistance, right? So then I would add another small vector, and that's force of the air, right? On the ball by what? The air? Yep, sounds good to me. So if I look at that, what's my net force now? Well, I have that, and I have that. Subtract those two, right? So now my net force is smaller than what it was before because it goes up, reaches its plateau, then it starts wanting to come down. That goes along with projectile, okay? And then the last one, after the softball reaches the maximum height, it falls down and speeds up. What's going on there?
It's less air resistance because it's falling down.
Yep,
He threw it up pretty high.
force and gravity is increasing, right? Force implied is decreasing, right? So my net force is now that way. And that would be force of gravity. Do we understand? Okay, let's get our handout out. And we're going to do 2 of these and we're going to stop and I'm going to give you some time to do your work.
The free body handout.
Yep, free body diagram. If you need to stand up and stretch for a minute, please do. Because I know it's after lunch.